Okay, so let us continue on the same topic, the separation of variables. So we've learned the last time that Laplace operator in 2D can be written as dr squared plus 1 over r dr plus 1 over r squared d over d phi d2 over d phi squared. And if we want to diagonalize this operator, we can just choose functions of the form I am phi. The eigenfunction of this operator. But in 3D, this Laplace operator is more complicated. So the radial part is very similar. But here we have an angular component of Laplace, which is something, and this angular component has a form theta and phi equals to 1 over sine of theta d over d theta sine of theta d over d theta. Maybe we can act on some function to write this unambiguously. Plus 1 over sine of theta squared d2 over d phi squared. Right? And we want to choose such basis of functions of theta and phi, so that they are eigenfunction of this operator. So it is in two variables, and we see that some part of this operator can be diagonalized. So we can say that if we consider, so we want that this Laplace operator acting on some function, let us call this some function y of theta and phi, equals to minus, we will find what sign is correct here. So So we want it to be eigenfunction of this Laplacian, and if you want to do this, we can start from asking it to be eigenfunction of this operator. So we can say that y of theta and phi is e to I m phi times some function of theta only. Or, in other words, we can say that any function of theta and phi can be expanded in a Fourier series as a function of phi. And then we study each Fourier component in phi, and this Fourier component has this form. It is it is this exponential times some function of theta only. So if you well, theta and phi. So if you substitute it into this equation, we will find that 1 over sine of theta d over d theta sine of theta d over d theta p minus 1 over minus m squared over sine of theta squared p equals to minus lambda p. So, and the question is, who is this p? What are the solutions of this equation, and what are possible lambdas? Like for which lambdas can we solve this? And so in principle, I will tell about the more general theory of such equations, like how to study it starting from the equation. But in this particular case, and actually it seems that we can do something like this in any situation when this equation has some explicit solution. So in this possible. So in this particular situation, we can use some tricks which will give some nice formulas for a solution of this equation without actually solving it. So, to show an example of this, we can go back to the 2D case. So in this 2D case, we want to find eigenfunctions of we want to find some nice expansion for this function as a function of angle, and we can do the following. We can notice that there is a green function. So there is a g which depends on z and z0, and it equals to 1 over 2 pi logarithm of absolute value of z minus z0. So and the consequence of this is that if we consider z is absolute value of z is less than absolute value of z0, if we consider such a disk, we put here z0, and consider a disk of smaller radius. So in this region, we know that Laplacian of g equals to 0. Z0 equals to 0. And we can now try to expand this green function in z. So z is less than z0. So we can write that g of z0 equals to 1 over 2 pi logarithm of absolute value of z0 plus 1 over 4 pi a logarithm of 1 minus 1 minus z over z0 plus 1 over 4 pi logarithm of 1 minus z bar over z0 bar. And since absolute value of z is less than absolute value of 0, we can say, and we can also substitute z in polar coordinates. So this is r e to I phi, and this is r e to minus I phi. So the Green function equals to uh, to uh, to constant like 1 over 2 pi logarithm of z0 plus sum of minus sum. So let us well, it is fine. So 1 over n 4 pi n z0 r to the power n e to the I phi. I n phi minus the same sum with a conjugate. So and we know that Laplacian acting on this gives 0. But let us now try to do the following. Let us try to act with r squared times Laplacian. So r squared times there. Yeah, thank you. Yes, thanks. So let us consider r squared Laplacian. It equals to uh, to r dr squared plus Laplacian phi. And so we know that this r dr squared plus Laplacian phi acting on the series. Well, let us write it like this. We will remove some scalars which we have here, some scalar factors. So we know that it is 0. But if we now act with the separator in each of these terms, r to the power n is an eigenfunction of r squared. And with what eigenvalue? So, who can tell this immediately? So, what is this? What happens if we act with RDR only once? Mm-hmm. Yeah. Hmm? Yeah. Thank you. So if we act with this, it will give just number n squared, and so we will have an inequality like sum of 1 over n z 0 to power n e to like n squared plus plus n phi. So here we have r to the n acting on e to the r n phi plus this sum, maybe so bar to the power n. So and these functions are linearly independent, so we can compare all these coefficients and conclude immediately that that this equals to 0 and this also equals to 0. So we found eigenfunction of this angular part of Laplace operator, and right, and so in this case we recovered just Fourier transformation on a circle. So this basis is used for the Fourier transformation, so it's not so interesting. But I wanted to demonstrate this idea, which I will now apply to the 3D case. Are there any questions about this? Minus and square. Yes. So in this case, we can diagonalize just d phi. Well, but everything is clear. It is a simple situation. So it's so this peculiarity that multiplicity is a tool for this one-dimensional equation is special for a circle, because if you consider some interval from 0 to pi, for example, all multiplicities will be 1. Okay, but now let us try to do the same for the 3D case. So we know that a green function of a Laplace operator is R. Just denote this R0. It is 1 over 4 pi 1 over R minus R0. So here we want to do the same thing. So we want to for absolute value of R less than absolute value of R0. So in a sense, so we have such wall, and we want so here is R0 somewhere. And so here it is axis z, x and y going somewhere. And here it's r0, and we are considering this equation, this ball r less than r0. Um, since everything should be function of theta and phi, we need to express this r in terms of r, theta and phi, and we also need to choose r0 in some way. So let us start from the following. So this vector r equals to z cosine of theta. R cosine of theta, r sine of theta, cosine of phi. It's z component, y component, and x component. Sine of phi. R sine of theta, cosine of phi. So let us first try so it is so there are components of R. So it is a Z component, a Y component, and X component. So it is R. So now we need to choose this R0. So we know that this will be solution of the Laplace equation for any R0 because because green function solves this equation. But if you want to find some solutions, we can start from R0, which is equal to which has only that component. So it is maybe for simplicity, let us take it 1, 0, 0. So it does not matter because everything is kind of scale invariant. There is no scale parameter, so we can study the simple case. So, and now the question is, who is this? What is in the denominator? So, square root. So, absolute value of r minus r0 is what? It is square root of square of r minus r0. So it is square root of r0 squared minus minus 2 scalar product r0 plus r squared. And in our particular case, so this scalar product equals to r cosine of theta. So it equals to a square root of 1 minus 2 r cosine of theta plus r squared. Okay, so we have this, and we want to do the same. So now we say that we can expand this green function. So this 1 over a square root of 1 minus 2r cosine. No, what? Which one? Yes. Yes, it is like in this case. So we wanted to study this z in this disk. So 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 we know that this object. We know that this object will be killed by Laplace operator. So this plus acting here gives 0. But and and now we want to do the same trick. So here we expanded this in powers of r, and let us do the same here. We see that when r equals to 0, it is 1, and then we can compute Taylor series in r, and the coefficients of this Taylor series will be some polynomials of theta. Order of n's coefficient will be n. So we can write that it is it is by definition. I don't know where to write this on these two dots. So by definition, it equals to sum from n equals to 0 to infinity r to the power n p n of cosine of theta. And we know that it is expansion of the gain function. So r squared. I will write the formula for this radial Laplace here. So r r squared dr squared plus 2r dr plus Laplacian of theta phi acting on this series. And now we can do the same trick. So we have in this radial part of Laplacian and this powers of n. Maybe, well, it is standard label for for indices of this polynomial. So probably let us use this. This is called L. And who can tell what is the eigenvalue of this operator when it acts on r to the power L? So it can be written actually as r dr times r dr plus 1. So yes, thank you. So we get that sum from L equals to 0 to infinity, L times L plus 1, so r to the L times L plus 1 plus Laplacian of theta and phi acting on PL of cosine theta equals to 0. Therefore, we know that this operator, Laplacian of theta and phi, acting on PL of cosine theta, equals to minus L plus 1. But So and maybe we can look at the first. So these tails are called Legendre polynomials. So the only disadvantage of this trick is that these solutions have a zero eigenvalue of d over d theta. So it is only hmm? Oh yes, thank you, thank you. In a sense that d over d phi of PL of cosine theta equals to 0. So in principle we can compute maybe zeros first and second polynomial. So what we need to do? We need to take this 1 over square root and expand it. So 1 over square root of 1 minus 2r sine of theta minus r squared equals to 1 plus 1 half 2r cosine of theta minus r squared plus so if we take second derivative of this, it will be 1 half 3 halves and 1 half, which is 1 of 2 factorial times 2r cosine of theta minus r squared plus r squared, and so on. So it equals to 1 plus r cosine of theta plus r squared, and here we need to see which terms are present. So there is this three halves times cosine of theta squared. So it is and here we have minus 1 half. Plus and so on. Which one? This?
We are expanding one minus x, everything to the minus 1 half.
Yes. Yes.
So it's minus 1 half, minus 1 half, minus 3 alpha. So those are minus.
No, but we are differentiating 1 over square root of 1 minus x. So if we compute the first derivative in x, there is minus 1 coming from here and minus 1 coming from.
But
So it's also plus because it is minus 3 halves and it is still minus x. So it is minus 1 times minus 3 over 2.
Okay.
Ah. Mhm. So it's, I think sure it should be correct. Mm. At least the answer is correct. So, mm. So is it fine? Mm. So, mm. And when we put x equals to 0, it is 1, 1 half, 1 half, 3 halves, so like this. Mm. So, okay. But it was there is this problem that in principle we found some eigenfunctions of this Laplace operator, but it corresponds to solutions of this equation only for m equals to 0. So in principle we can already solve it, but only for this particular case. And it is clear why it happened because we have chosen one parametric R0 which was pointed towards z, so it was symmetric under rotations around this axis. And if you want to get something non-symmetric, we should choose some other R0. Uh, uh, so uh, we need to break this rotational symmetry. And there is one trick which allows to do this. Maybe it is the simplest way to get nice formulas. And this trick is to consider a complexified value of R0, because anyway, it is some series in R, so we don't care if R0 is complex or real, so we can choose such a nice form of R0, which is 1. Let me think. 1 I epsilon and epsilon. So my thing is then R0 squared is still 1. And the scalar product of R0. So who can tell what is the scalar product of R0 with R? Oh, so but it should be simple. What is the problem to compute this?
R plus theta.
Mm-hmm.
I guess
Well, we can combine everything. So I phi sine of theta, right? Because it is cosine plus I sine. And so if you substitute this into our formula, we know that this expression will also be killed by a radial component of Laplacian. So we know that there is this 1 minus 2 r cosine of theta plus epsilon e to the I phi sine of theta plus r squared. So we know how to expand this because we know the definition of Legendre polynomials. So we can say that it is a sum from L equals to 0 to infinity r to the L PL of cosine theta plus epsilon e to the I m phi sine of theta. And now we can expand this also as a series in epsilon. So it is a sum from L equals to 0 to infinity, a sum to R to L, sum from m equals to 0 to. So these polynomials are of degree L. It follows from the definition. So it is a sum from 0 to L. And it will be just Taylor series of this polynomial. It will be 1 over m squared or m factorial. Because right here it will I m phi.
So on the expression before this one, if we put the I and phi,
Yeah, thank you. It's just I phi. So here we will have a sine of theta to power m. And here we will have m's derivative in theta, in cosine of theta. dm over d cosine of theta to power m pl of cosine of theta. And and I missed epsilon to power m. And again, we can say that because of the same argument, we see that
could you give us the formula for Piano?
it is a separate problem to derive explicit formulas. So it is clear that in principle the series defines all the spells. We can compute each of them, right? So we can get some formulas from this series, but we also derive this so-called Rodrigues formula, which is explicit expression for pairs, but it will be a bit later. So But for now, we just think that we know PLs and we construct these functions from them. Right? So we can define such functions PLM of theta. Well, maybe of cosine of theta. Actually, people often call this cosine of theta x. So, probably we'll switch to this notation. So if we define this functions PL m like 1 minus cosine squared of theta to m over 2 d over d cosine theta dm to so it's in definition. So they are called associated Legendre functions. So they are called functions because PLs were just polynomials of cosine of theta, but these functions, if you try to express them in terms of cosine of theta, will contain also sine, which is sometimes it is square root of 1 minus cosine of theta squared. So they are not necessarily polynomials; they are just some functions. So if we introduce this notation, then we see that again this r dr squared plus r dr plus plus Laplacian of theta and phi acting on the series. Now series in two variables. Oh, sorry. 7 to m e to the im phi p l m of sine of theta. So the separator acts by 0. And we can also say that introduce the following notation. We can call this YLM of theta. So we can repeat essentially the same argument as worked for Legendre polynomials, and it gives us that Laplacian of theta and phi plus L plus 1 acting on this y Lm of theta and phi. Equals to 0. And if you write it in terms of, if you write it as in terms of equation for this PLMs, we can say that it is equivalent to a statement that 1 over sine of theta d over d theta sine of theta d p l m where d theta minus m squared over sine squared of theta equals to minus L plus 1 PLM. Like this, right? We know that this that these functions are eigenfunction of this angular Laplace operator. So probably, so it's a definition. And there is also a statement that they form they form a basis in functions on a sphere. So maybe we can call this theorem. This YLMs. So we should also define that if m is less than 0, then YLM is e to minus im phi PLM of cosine theta. So this theta and phi form a basis in functions on S2 on a sphere. Actually in L2 of S2. Square integrable functions on a sphere. And it is so if we start from such construction that we took a green function and tried to expand this, it is easy to understand. Kind of, I don't know if you can call this the actual proof, but it is well, I will call it a kind of proof. Because we can, so if you want to use this trick with a green function, we can consider some function which is let us consider some a function of r, theta, and phi. Inside this unit ball, and say that this function is some function of r times phi of oh, maybe it's bad notation. Maybe let's call it fr. No, it's g of theta and phi. And we can say that this function can be recovered from its Laplacian. So we can say that on this f of r, g of theta and phi is the integral over dr prime Laplacian of f of r theta and phi times gain function of r prime theta prime phi prime times gain function of r prime. And well, let us also choose this f of r such that it is 0 for, so f of r is 0 for maybe no, maybe it's too much. Let us choose this f of r in such a form that it is 1 at that it is 0 for, so r f of r it is 1 at r equals to 1, and decays to 0 quite quickly for r for some decays to 0 quite quickly when r is greater than 1. So we can well we will compute this this function at 1, which is 1. So we can we can write this g of theta and phi, this integral of Laplacian of f times gain function, and this integral goes over the domain r is greater or equal than 1, and to something to r prime to no, not r prime, but some r is less or equal to some r. So this integral can be computed somehow, but the main point is that this gain function has this expansion, which comes from this formula. So let us move here, maybe here. So it is 1 over 4 pi integral in this r greater or equals than 1, less or equals than r, and here it is dr prime 1 over square root of 1 minus 2 r prime, and here we need to compute a scalar product of r and r prime. So r is r cosine of theta, r sine of theta sine of phi r sine theta cosine of phi. And for r prime, we have r prime cosine of theta. So here it is r prime. R prime theta prime sine phi prime r sine theta prime cosine phi prime. Let me change the equation. So if you compute the scalar product, we will have cosine of theta cosine of theta prime plus sine of theta prime and here this will be a cosine of phi minus phi prime. I forgot. Also here we have absolute value of r, which we use here is 1. So absolute value of r is 1. It is r prime. So we should write it like, we should put r prime here and write it like this. Minus 2 1 over r prime plus 1. And here we have this Laplacian of f of r prime theta prime phi prime. So if we now expand this 1 over square root using the definition of this Legendre polynomials, we will have so 1 over 4 pi integral this dr prime Laplacian of f r prime theta prime phi prime sum of r prime to minus l pl of this argument. So we see that when we compute all these integrals, it will be some combination of some coefficients CLM times YLM of theta and phi. So and it's kind of the end of proof. It tells us that we can we can take take our function and write it as a series in this YLMs, which are called spherical harmonics. Are there any questions about this? So, but hmm?
Shouldn't be one of the five first.
uh,
Wouldn't be first name.
yes, yes, NSL minus one. Yes, should be here. Oh, actually, no. I thought that one should be a bit more careful here because we need to find the precise expansion of this expression in terms of spherical harmonics. So yeah, I didn't think about this well. Actually, on this equation is not obvious, and uh, because here we have a scaled cosine of theta, so. Mm, So probably there is a gap here which I don't know how to fill in right now, but we can derive the statement about completeness of this basis later from the general theory of such equations like this. So it is true in any case, but we need to think more about this proof. Sorry. So, uh, so here it's so this one is not obvious and it's not a complete proof. So maybe let us come back to this later. Uh, so I know. So. Hmm? Hmm? Could you say it again?
In cases they're just proven the generator part and not the independent part.
What do
Because a basis needs not only to generate the space but even to not be to be independent.
No, but it is obvious that they're independent because they behave differently with yes, and they are also eigenfunctions of this operator with different eigenvalues. So these L's are positive, and there is no way that they are dependent. So. Now let us go to the question about explicit formulas. Mm. So when we see this definition. So let us study Legendre polynomials because Legendre functions are just derivatives of them times something. So the main question is what is the formula for PLs? To get this, we can use complex analysis. If you want to compute coefficient of expansion of some series, we can multiply it by z to minus n minus 1 and compute the residue. So we can rewrite this formula like this. So PL of x is by definition 1 over 2 pi I integral of dz over z n plus 1 times L plus 1 1 over square root of 1 minus 2 zx plus z squared. So in principle, complex analysis might suggest us to deform this integration contour somehow, because it's unclear how to compute this residue, but maybe it could be simpler to compute the integral about around the branch cut of this. But actually, what we need to use here is this geometric factor that all curves of degree 2 are actually CP1s. Or it's another statement that if you have a curve of degree 2, it can be drawn with one kind of a strike of a pencil, like it is some ellipse. So if you have some, you should compare this. So if you have some curve of the form x cubed plus ax plus b, then it might have this form. So it can consist of several pieces. But if you have something like y squared equals to 1 minus 2 z x plus z squared, this curve is just some kind of ellipse. So I'm introducing this new variable y, which is square root of 1 minus 2zx plus z squared. And say that the object which we live on is actually not a complex plane with some curve, but it is something defined by this equation. So we can write that this PL of x is 1 over 2 pi I integral of dz over z L plus 1 dz over y z plus 1. And so it is something quadratic, and the statement is it's a kind of the same statement as formulas for Pythagorean triples, integer numbers that satisfy a squared plus b squared equals to c squared. So it's the same trick. So So if you want to write some rational parameterization of this z and y in terms of one variable, so we want mm, we want to write a y uh, as y of t and z. No, not t. No, it's fine. And z of t. Mm. So if you want to do this, we can perform the following trick. We can find one point which is some fixed point which you already know, and then intersect this second degree curve with some line, like uh, uh, like this. And we know that since it is a degree 1 curve and degree 2 curve, they have only two intersection points. So we can say that that this second point is parameterized by the by the by this angle, by the slope of this curve. So this phi said that cosine of phi equals to t. So we know that there will be only one intersection point, except this one, and it will allow us to write y of t and z of t as some explicit functions. So let us try to do this in this case. So in this case, we should choose. Let us choose this point as y equals to -1 and z equals to 0. So it is so. Uh, uh, then the slope of this curve, which we denote t, will equal uh, to z over y plus 1. Mm, let me rearrange this. Uh, well, we still have some space. So we want to introduce this variable and express y of t and z of t. To do this, let us look at this equation, and let us move 1 to the left-hand side. So we see that y plus 1 times y minus 1 equals to z uh, 1 z minus 2x. So 0 over 1 plus 1 is t. We see that 1 minus 1 equals to t. Z minus 2x. So let us now substitute z in terms of y. So, so this is at 1 y minus 1 equals to t. No, sorry, let me think. I actually forgot what is the correct variable, t or t inverse. So maybe it is 1 plus 1 over t. Plus 1 over t. Maybe no. So the substitute here z in terms of t and y. Ty plus t minus 2x. So and then y 1 minus t squared equals to 1 plus t squared minus 2tx. So there is the formula for y. Or 1 minus t squared. So this can be written as 1 minus, so okay, it is 1 minus t squared, 2t squared minus 2tx. So it is equal to 1 plus 2t minus x over 1 minus t squared. Well, anyway, there is a formula. And if we now compute, so now we want to compute who is t. We already have this rational parameterization for y, and we need to use this formula to find z. So z equals to z equals to t 1 plus oh, sorry. Finally, the correct variable was t inverse, but we will fix it easily. So here is this t here, which still have. So it is. So we can write it as. Mm, let me think if it is correct or not. So let us introduce a new variable t, which equals to this t inverse, t big, which is t inverse. We could do this from the beginning, but I forgot the correct change of variables. So if we do this, but I just want to put point z equals to 0 at t equals to x. You'll see why it is nice. So if we do this, then z will equal to uh, to t inverse t minus 2 1 minus t squared. Here is so finally it is t. It is x minus t over 1 minus t squared. Okay, so it is one formula, and another formula for y should be oh, and I don't know why I decided to write it this way, because we had a split square in the numerator, and this is what we actually like. Uh, so, sorry. So y will equal to minus t minus x, this big T minus x squared over 1 minus t squared. So what happened here? We found these formulas which solve this quadratic equation. So we know that on this y of t squared equals to 1 of minus 2 z of t x plus z of t squared. And we cannot do anything similar to this for this elliptic curve. So if you want the analog of such formulas, then in this case it should be this equation for the Weierstrass plus function that is p prime squared equals 2p cubed plus g 2p plus g3. So this curve can be parameterized only by an elliptic function. And yes, sorry, I forgot this. Yes. Uh, so, but and you see that so if we perform this change of variables, then integrals which involve square root can be reduced to the integrals of some rational functions. So this is why all such integrals with square root of second order polynomials can be expressed in terms of at most logarithms. So this is why we can integrate such functions. But let us apply this in our particular case. So the only ingredient which we need is which is dz. So we need to compute this derivative. So dz equals to so it equals minus 2 dt over 1 minus t squared plus plus minus p minus 2 t squared dt over 1 minus t squared squared. So it is in total it is minus 2 over 2 dt over 1 minus t squared squared. So we also need this to compute that integral. So let us take all this and substitute into our formula. So PL of x is equal to 1 over 2 pi integral around so we see that it is integral around 0. And here, we see that z equals to 0. So one of the points when z equals to 0 corresponds to x equals to t. And y in this case is oh, so it's integral around t. We need to substitute dz, which is minus 2 dt over minus t squared squared. Then power of z. And y. Which term?
Second item. Minus, maybe you should multiply by the x minus 2.
Yes, it's true. Thank you. Yes, so it is t x minus t. Yes, it's true. And so it will give, what will it give? T squared will, so t squared is cancelled. So what is what remains? Mm. Looks it looks strange. So it seems that it is minus minus 2. 1 minus tx, which is strange. Maybe it's fine. I actually forgot. Hmm?
Suppose of these two in the same because
So,
you take the differential of t square and multiply by the first t. So in the second
mm,
time you choose here.
yes, it is. It should be 4. Yes. Thanks. And now, so maybe it looks better. It will be minus 2 t minus x squared, right? Mm, yes, it is.
There's no x
Well,
squared.
hmm?
There's no x squared. Maybe.
Yes, it is true. So
So there is a minus.
let me just write these expressions. sorry for this. So it is 1 minus t squared. Here we have minus 2 plus 2t squared plus uh, plus 40 t squared minus 40x. It is very strange. Sorry, it looks like I made some stupid mistake somewhere. Oh, maybe let me just quickly check this formulas in mathematics so that.
E equals 1 minus y over d in the
Hmm? Where? Oh, let me just check the formulas. So I made some mistake in the parameterization, I think. So yes, made mistake when I wrote this as t minus x. It is not true. It was not well. It was not a complete square, and it is still not a complete square. So yes, so one mistake is here, and then another probably. Uh, I don't know. Mm, So yeah, so this is one on the So no, so this was just wrong. It does not equal to this formula. So correct formula is y equals to minus 1 plus t squared minus 2tx over 1 minus t squared. And here this equals to so dz equals to mm, 1 plus t squared minus 2tx over so, minus 2 uh, divided by minus t squared squared. So, sorry. Uh, correct formulas are this. So if you now consider dz over y, we will have this factor dt over 1 minus t squared squared. Mm, sorry. And here no, divided by just 1 minus t squared. So hmm? Yeah, we don't need we don't have this. Yes, sorry. So the dz equals to this. Yeah, really equals. So dz over y, dz over y is 2 dt over 1 minus t squared. Sorry for those mistakes. And so this term becomes actually simple, and remaining term, which was originally simple, it was z to power l plus 1, mm, is now this expression. So probably so is there any question here? Let me think. Okay, so we need now to compute this integral around x equals to t, and this is that it can be written as 1 over pi I. Probably there might be some question about sign. Let me actually check. Maybe. No, there is no question about signs. So we just need to compute this integral around dt. But this integral is what? It is 1 over 2 pi I. And here let us compute the power of 2. It is 2 to power minus L. This integral dt over t minus Oh, I don't like this x minus t. Is it correct or not? Or maybe. Maybe there is a question about signs. Let me just do this. Because there is a question which branch of the square root should we take, and so if we substitute t equals to x and send and so yes, if you substitute t equals to x, probably it, yes, I think I forgot precisely what can be the tricky moments here, but it seems that we should do this. So we have this, and we have t minus 1 t minus 1 to power L, t squared minus 1 to power L. So if we now compute this integral by residues, we get that it is 1 over 2 to power L factorial d d n over d L over dx L x squared minus 1 to power L. And this is called Rodrigues formula. So, it is something very explicit. So you can expand this x minus 1 to power L using binomial coefficients, and then compute this derivative explicitly. And and of course it is computationally efficient, and it also has various nice properties which we'll study on the next time. Okay. So sorry for the mistakes. Do you have any questions about this?
Should we remember it for the exam?
This formula. Well, if it is so simple as this one, then of course one should remember it, or at least be able to derive it. But actually, no, not necessarily. It's not necessary to remember this coefficient, but better to know this formula itself. Maybe for formula of the first two non-trivial polynomials. Okay, so do we have any questions about this? Okay, well, thanks for your attention. We'll see you the next time.